Hello and welcome. In this video, we're going to be talking about integrals that result in natural log, or integrals that end up simplifying to have natural log with them. This is a great follow-up to the video on derivatives involving natural log, which is 5.4. So let's go ahead and jump in. So what we learned in the previous section is that if we take the derivative of natural log of x, we get 1 over x. If we take the derivative of natural log of something else, let's just call it stuff, the derivative of natural log of stuff is going to be 1 over that stuff times the derivative of that stuff, if we're using the chain rule in a circumstance like that. One thing that we didn't talk about before that we're going to need to talk about before we get into integration is that natural log of x has a very specific domain restriction that all of the x values that we plug in have to be positive, because natural log of a value is exponents that come from e. E to any power will never be negative and it will never be 0. And because of that, that means we also need to think about the derivative over here has a different domain restriction. In 1 over x, we're allowed to have negative values, but we aren't allowed to have x be equal to 0. So we have different domains, but we're saying that the derivative of this natural log function is equal to 1 over x. And we're going to say today that we can actually work backwards, and the antiderivative of this is going to give us natural log. And that relationship makes sense to be able to go derivative, antiderivative, back and forth between those two things. But we need to deal with this domain issue. To remedy this, what we do is we need to make sure that any number that we're going to put into a logarithm is positive. So what mathematical tool allows us to make things positive? Absolute value. So the way that we remedy this issue of inconsistent domains between these two functions that we're going to be going back and forth between is that we include absolute value when we take the integral of 1 over x dx. So when we take an integral, we're asking ourselves, this is the derivative of what function, right? We're finding the antiderivative. We're undoing the derivative. Well, this is the antiderivative of natural log, but to make sure we have the same domain, we put natural log of the absolute value of x. If there are more things going on, we may need to use u substitution. So we may need to deal with rearranging this or defining u to be something so that we have u in the denominator and the derivative of u in the numerator. And that would give us the natural log of the absolute value of u plus c. This particular version you're going to understand a little bit more naturally when we just use u substitution. The way it's written here at first glance is a little bit confusing, but I think it'll make more sense once we jump in. So when we're evaluating an integral, things that we want to think through first. Can I evaluate this integral in the current state that it's in? We should always ask ourselves that first. What I mean by that is that if we just had x squared plus 3 and we were integrating that, we don't need to use u substitution. U substitution should not be the first thing we think. The first thing that we think is, can I evaluate this in the state that it's in? And this purple one that I just drew, I can just apply the power rule and I could find the antiderivative without having to do any more complicated work. Now, if I look at this particular problem here, I can't just evaluate this. I can't just apply 1 to or add 1 to the exponents and divide by that exponent. There are multiple functions happening here. I have a composition of functions. So that basic idea isn't going to work on this problem. The next thing I'm going to ask myself is there anything I can simplify to make it so that I could just evaluate that? So could I simplify anything here? And what I mean by that is if we had, I don't know, x over x to the third power dx, we could simplify this, right? This would become the integral of 1 over x squared dx, and we could find the antiderivative of that using the power rule. So first, can I evaluate it the way that it's written? Second, can I manipulate what's there? Could I use trig identities? Could I use division? Is there anything that I can do in the current state that it's in to rewrite it so that I could just integrate it? And then we get to u substitution. So when all else fails, we're going to jump into u substitution. So I want to let u be the more complicated function here, which is going to be my denominator. U equals x squared plus 1. So du is going to be 2x dx, and if I solve for dx is going to equal du divided by 2x. So I'm going to replace x squared plus 1 with u, and I'm going to replace dx with du over 2x. So let's go ahead and rewrite this integral. We now have the integral of x over, our new denominator is u, and instead of dx, du over 2x. So does anything simplify here? Sure, these x's divide out, and the 2 I can go ahead and bring in front of the integral. So now I have the integral of 1/2 times 1 over u du. And the point we're trying to make here is that this is the derivative of natural log. So to work backwards, the antiderivative of this piece here would be natural log of the absolute value of u. And remember that absolute value is coming into play to make sure we don't have any issues with our domain. We still need our 1/2 in front, and we still need our plus c at the end because this is an indefinite integral. So let's work through some more practice, but we're manipulating as needed so that we can use u substitution. If when we're using u substitution we end up with 1 over u, that's going to take us to natural log of the absolute value of u plus c. Okay, so I'm going to ask myself some of those same questions here. When I look at this integral, can I integrate it in the current state that it's in? Can I apply what I know without changing anything to do that? If you can, go ahead and do that. If you're not seeing it, let me see if I can help you here. If we take the 5, which is just a scalar, and we move it in front, now can we evaluate this without manipulation? And the answer there is yes. What is 1 over x the derivative of? It's the derivative of natural log. So the antiderivative here would be 5 times natural log of the absolute value of x plus c. When I look at number 2, I'm asking myself the same question. In the current state that it's in, can I evaluate this? Well, this is not just 1 over x. It's 1 over a function that involves x. So I can't just jump immediately to natural log. There's nothing I can divide. There's no way I can simplify this. So that leads me to think maybe I need to use u substitution. So if I let u equal 3x minus 2, then du would be 3 dx. So dx would be du divided by 3. So I can rewrite my integral as the integral of 1 over u times du over 3. And I can simplify this to be 1/3 times the integral of 1 over u du. And now I can actually evaluate this integral, 1/3 of natural log of the absolute value of u, I'm getting ahead of myself here, plus c. And now I can plug back in what u was, 3x minus 2, to get to my final answer. This integral is going to equal 1/3 times natural log of the absolute value of 3x minus 2 plus c. Okay, number 3. First question, can I evaluate this in the current state that it's in? No, there are multiple functions. There's a composition of functions. I have a function in the numerator and the denominator. I can't just apply the power rule. There's no special trick that works on this function or on this expression here. So I can't evaluate it as is. I can't split this up or actually divide or do anything to simplify it. So then I'm going to move towards u substitution. So I'm going to let u equal the more complicated function, which is the denominator. So du is going to equal negative 3x squared dx. So dx is du over negative 3x squared. So if I rewrite this integral, I still have x squared in the numerator. I now have u in the denominator and du over negative 3x squared. So things that simplify the x squareds, and I'm going to take the 1/3 in front. So I have negative 1/3 times the integral of 1 over u du, which is going to equal negative 1/3 times natural log of the absolute value of u plus c, which is going to equal negative 1/3 times natural log of the absolute value of what u was, which is 3 minus x cubed plus c. So we now have a new tool that we can use when we're evaluating integrals. This is not always going to be the case. We are focusing on a lot of examples that end up giving us 1 over u inside our integral or as our integrand, but every single problem isn't going to result in this. So remember all of the things that you learned before. Start by thinking, can I evaluate this in the state it's currently in? Can I simplify this in some way? If not, can I use u substitution to help me out? Then go from there. But keep that in mind as we work through some more samples. Okay, if you're starting to feel confident, go ahead and pause the video and see how you can do on 4, 5, and 6. Otherwise, work through these problems with me. On number 4, I can't simplify and I can't integrate in the state that it is currently in. So I'm going to use u substitution. I'm going to let u equal 9 minus x squared. So du is going to be negative 2x dx. So dx is going to be du over negative 2. And I'm going to rewrite my integral. The integral of x over, not just u though, the square root of u, or u to the 1/2 power, times du over negative 2x. And then I'm going to simplify this. My x's divide out. Negative 1/2 can come in front. Negative 1/2, the integral of u to the negative 1/2 power du. Now this problem actually is something we could have solved in Unit 4. There is no natural log component because I didn't end up with 1 over u. I ended up with 1 over u to the power of 1/2. So again, don't forget the things that you learned before this. So if I integrate this, u to the negative 1/2 power, if I add 1 to that, I get u to the positive 1/2. And if I divide that by our new exponent, that's the same thing as multiplying by 2. So this is going to simplify to be negative u to the 1/2 power plus c. If I multiply this 2 and this 1/2. And I'm going to go ahead and plug back in what u was. U was 9 minus x squared. Now on number 5, asking ourselves those same questions. This integral, or the integrand here, can I integrate it in the state that it's currently in? No. Could I manipulate it? Well, yes, cosine of theta over sine of theta is cotangent of theta. But I want you to think about whether or not we know what the integral of cotangent of theta is. We know that if we had the integral of negative cosecant of theta, that would result in cotangent, but we don't actually know how to integrate cotangent of theta. So it's not going to benefit us to rewrite this as the integral of cotangent of theta d theta because we don't know how to integrate that. So that leaves me with u substitution. Why don't we let u equal the denominator? So du is going to be cosine of theta d theta. So d theta is du over cosine of theta. So this integral is going to be equal to cosine of theta over u times du, but I didn't write that, over cosine of theta. My cosine of thetas divide out, so I'm left with the integral of 1 over u du, which is going to give me natural log of the absolute value of u, plus c, and then I can plug back in that u was sine of theta. So now we actually just derived the integral of cotangent of theta is equal to natural log of the absolute value of sine of theta plus c. So now we do know how to integrate cotangent. And in fact, if we wanted to figure out how to integrate tangent of theta, we could just look at the reciprocal of this and work through it in the exact same way. We would let u be cosine of theta because that would be in the denominator, and we'd work through it in almost exactly the same way and get a very similar final answer. Okay, number 6. Can we integrate it in the state that it is currently in? No. Can we simplify? Yes. This is the same thing as the integral of x squared over x minus 4 over x dx. Well, that's the same thing as x minus 4 over x dx. And now we still don't need to use u substitution. If I integrate x, I get x squared over 2. If I integrate negative 4 over x, I'm going to get negative 4 times the natural log of the absolute value of x plus c. So keep in mind all of those different pieces when you are working through an integration problem. Don't forget everything that we learned before just because we're learning something new now. So I want to wrap up this video and talk about different approaches to integration and look at some samples of working through those problems. So we've talked about U substitution, and we're going to talk more about that again. But one thing I want you to notice when we have a polynomial or a rational function, something that we can do that may simplify our entire process is identify when we can divide first. We can always divide first if the degree of the numerator is greater than the degree of the denominator. So if you look at this problem here, the numerator has a degree 3, the denominator has a degree 1. So we can actually divide those two expressions, or we can divide that rational function to come up with something that is similar. Now that means we have to look back and think through a little bit of algebra 2, either using long division or using synthetic division. I will walk through both of those types of division here. And then that'll give us an expression that is simplified. So we're not actually going to go all the way through the integration, but we are going to review the algebra 2 part here. So I could rewrite this. I'm going to do long division first. The reason I'm going to do long division first is because most people forget synthetic division, but long division sticks with you because it ties back to when you originally learned how to divide in elementary school. So just like if I was dividing 3 into 5,095, I would ask myself, how many times does 3 go into 5? And the answer would be 1. So I would multiply 3 times 1 to get a 3 here. Here I'm saying, how many times does x go into x to the third? Well, it goes in 2 more times. Or what do I multiply x by to get x to the third? I multiply it by x squared. That would give me x to the third. I'm going to multiply it also by 5. So times x to the third plus 5x squared. And then over here, the next thing I would do is subtract and then bring the next digit down. So we're going to work through that same process now, but with our polynomial expression. So we're going to subtract here. X to the third minus x third is 0. 0 minus 5x squared is negative 5x squared. And then we can go ahead and bring down the other two terms. Now I'm asking myself, what do I do to x to get 5x squared? Well, I need to multiply it by negative 5x. That would give me, I don't want this line here anymore. That would give me negative 5x squared. There we go. That would give me negative 5x squared minus 25x. Again, I am subtracting negative 5x squared minus negative 5x squared. This becomes addition, so this becomes 0. Negative 6x minus negative 25x. Again, we're doing a double negative situation here, so this is going to become negative 6 plus 25, which is going to be 19. So 19x minus 20. What do I multiply x by to get 19x? I multiply it by 19. That's going to give me 19x minus plus 95. And then I'm going to subtract here. 19x minus 19x is 0. Negative 20 minus 95 is negative 115. Now, when you were first learning how to divide back in elementary school, if something didn't divide evenly, what you usually did was write an R and say there was a remainder of something. In Algebra 2, you learned that your remainder gets put over the thing you were originally dividing by, x plus 5. So this could be rewritten instead of this as x squared, that's my first term, minus 5x, green term, plus 19, plus, or I guess minus 115 over x plus 2. Okay, let's look at that same problem using synthetic division instead. Again, long division is the one that's usually easier for people to remember the process for, but synthetic division, as long as you're dividing by a binomial, is going to be more efficient. But let me go ahead and set up synthetic division here. So when you're doing synthetic division, you only put the coefficients. So the coefficient of x to the third is 1, the coefficient of x squared is 0, then -6 for the x, and minus 20. And on the outside, you put the opposite of what you're dividing in. So the very first thing that we're going to do is bring our 1 down. We're going to multiply -5 times 1 and write that over here. And then we're going to add these two things together. That's going to give me -5. Now I'm going to multiply -5 and -5 to get 25 and add these two things together. That's going to give me 19. Now I'm going to multiply -5 and 19. That sounds familiar. Seems like we did something really similar with long division. That's going to give me 95. And if that's going to give me -95 since that 5 is negative. That's going to give me -115. And then you can see these are the same, right? 1 is going to be my coefficient with now we're going down 1 degree. So this is going to be 1x squared minus 5x. Keep decreasing your exponent by 1. And again, this value will be our remainder over the factor we were dividing by. So either way, you can get the same answer, whether you use long division or synthetic division. Synthetic division is typically much faster, but long division is the one that's a little easier to remember the process for. So why is it helpful to divide first? If you look back at this problem, let me erase here so it's easier to see. If you look back at this problem, let's think about the ways that we have learned to integrate. We can't integrate it the way that it is. I can't just apply the power rule. There's multiple functions here. I can't, other than the way that we just talked about simplifying, I can divide first. There's not any other way that I could really simplify this at all. And then if I tried to use u substitution, I would have to let u be the numerator, and the derivative of that, my du, is going to have an x squared in it, and there's no x squared anywhere else. So u substitution is not going to work here either. But by taking the algebra 2 skill of long division or synthetic division, dividing as a whole, we can change that integral to become this integral. And this integral, we could integrate just simply using the power rule. So I could add 1 to that exponent. I can add 1 to that exponent and divide. I can give 19 an x. And then this last piece is going to be my natural log piece. So this is really, you can think about it as -115 times the integral of 1 over x plus 2 dx. That piece is just going to become -115 natural log of the absolute value of x plus 2 plus c. And I know some of you might need to do u substitution to get there, but the goal here wasn't that we did this problem all the way through, but that you can see the benefit to dividing first. If you divide first and everything divides evenly, you're going to end up not having to have natural log at all. If you divide first and there's a remainder, your remainder is likely going to have natural log as a part of its component. So the very first thing we're always doing is identifying if we can integrate it as is. Then we're saying, is there something I can do to simplify it? And long division or synthetic division, dividing, may be that thing that we can do to simplify. Then we have individual terms that we can integrate one at a time, and that's going to make our lives easier. So what happens in a different kind of problem? Let's look at some other types of problems and the ways that we can work through those. So we spent some time talking about regular u substitution, and when I look at this example here, I know that I'm going to need to use u substitution because I have absolutely no idea how I'm supposed to integrate natural log of x, let alone 1 over natural log of x. So here I would let u be this complicated function that I don't know how to take the derivative of, or that I don't know how to integrate. So I'm going to let u be natural log of x, which means that du is 1 over x dx, which means I'm going to multiply both sides by x. I'm going to get that dx is equal to x du. So let's see what happens when we rewrite that integral. We would get 1 over x times u times x times du. So those x's are going to divide out, and we would just end up with the integral of 1 over u du, which we could integrate to get natural log, as we have already talked about. So this final answer here would end up being the natural log of the absolute value of the natural log of x, since this is what my u was, plus c. Now, we also talked about in a previous video that sometimes u substitution needs an extra little push to get us there. So if we look at this problem, we could expand the denominator. I don't know that that's going to help us. If we take the derivative, we might be able to work through it that way. We could also rewrite this as the integral of 2x times x plus 1 to the negative second power. And then if we use u substitution here, we would let u equal x plus 1, so du is going to equal dx. Here's what happens when we do that. We have the integral of 2x times u to the negative second power times du, but we still have this x left over. And if you remember what we talked about before is that you could just solve this for x. X is going to equal u minus 1. So this would be, I'm going to move the 2 in front. The integral, 2 times the integral of u minus 1 times u to the negative second power du. And then we could distribute. And now this is something we do know how to evaluate. So that's often referred to as change of variable number 1, which just means you have to solve for x so that you can rewrite this to be completely in terms of u. The way it is currently, you can't rewrite it to just be in terms of u like we could with regular u sub. So for regular u substitution, after we just plug in u and du, we just end up with something that doesn't have any x's anymore. Change of variable number 1, after we substitute in, we have something that still is in terms of x, but we can just solve u equals x plus 1. We can solve that for x and directly substitute in what we know x is. That's called change of variable number 1. Let's see what happens on change of variable number 2. So as it's written, I can't integrate it. I can't do anything to simplify it, so I'm going to let u equal the denominator here, 1 plus the square root of 2x, which means that du, and this actually I'm going to rewrite as 1 plus 2x quantity to the 1/2 power. If I take the derivative of this, the derivative of 1 is nothing. The derivative of 2x to the 1/2 power is 1/2 times 2x to the negative 1/2 power times the derivative of the inside, which is 2. And this is all with respect to x. So du is, this 2 and this 1/2 will go away. They'll multiply to be negative 1. This. So if I solve for dx, I get du times 2x to the positive 1/2 power. If I divide both sides by 2x to the negative 1/2 power, it'll just go into the numerator. So here's the problem. If I try and rewrite this integral, I get 1 over u, but then I get du times 2x to the 1/2 power. I don't know what x is here, so we sort of need to manipulate this a little bit more. It isn't that our original integral still has an x component in it, it's that our du has an x component in it. So what we can do is we can substitute. We know that this, I could probably manipulate u equals this. I could probably manipulate this to isolate the thing that I need to isolate. So what I need to isolate is 2x to the 1/2 power. So if I solve u equals 1 plus 2x to the power of 1/2, for this piece, I would just get u minus 1 equals this. So I could rewrite this as the integral of 1 over u du times u minus 1. And then I could simplify that. If I just multiply these two things together, that would end up giving me u minus 1 over u, or u minus 1, let's write this to the negative first power, du. We could simplify that and follow a similar process as we did for change of variable number 1. So the key things in this lesson, first of all, don't forget all of the things that we have learned before this lesson. You can use regular u substitution. It's not always going to result in natural log. You can change the variable if you need to. You can evaluate, or you can simplify your process by using long division first. You can still use the power rule. You can still integrate using different trig properties. The one big tool that we added to our tool chest today is that the integral of 1 over x dx, the integral of 1 over x dx, is equal to natural log of the absolute value of x plus c. And if there's a more complicated function happening, you can use U substitution to help you find that antiderivative. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.